Hey everyone, welcome back to The Explainer. Today, we're jumping straight into a totally classic algorithmic challenge. It's one that shows up literally all the time in technical interviews. You might know it as Leetcode 771 Joules and Stones. We're going to dive right into this because it's just the perfect illustration of how choosing the right data structure can take a sluggish, repetitive piece of code and turn it into something lightning fast and, honestly, pretty elegant. We'll be breaking this down step by step, mirroring the exact progression you'd go through in a real technical coding interview, starting with understanding the core rules and working all the way up to optimizing our final code.
So here's our roadmap for today. We're going to start with the Joules and Stones problem itself, then look at the brute force approach, explore the optimized hash table approach, write out our actual Python solution, and finally, wrap things up with a quick summary.
All right, let's get into section 1, the Joules and Stones problem, understanding the rules. Okay, before we write a single line of code, we need to establish the basic premise and the constraints we're working with. So here is the core objective. How many of your stones are also joules? Just picture this. You've got this big bucket of rocks, and you need to figure out which ones are actually valuable gems. In programming terms, you're just handed two text strings. One string represents the types of stones that are officially considered joules, right? So each character in that string is a unique type of joule. The other string represents all the stones you actually have in your possession. Your goal is simply to count exactly how many characters in your stone string also happen to appear in your joule string.
Now, you absolutely have to watch out for this one crucial constraint from the problem statement. The letters are strictly case sensitive. A lowercase a and an uppercase a are treated as completely different types of stones. So if your joule string says only a lowercase a is a joule, then any uppercase a you find in your stone string doesn't count towards your total at all. Our sources actually point out that this is a super common pitfall. If you forget about case sensitivity, or if you just use a function to lazily convert everything to lowercase, you are going to get totally incorrect counts. You've got to treat a and a as completely distinct entities.
Moving right along to section 2, the brute force approach and the trap of nested loops.
Let's think about how a beginner might naturally, but, quite inefficiently, try to solve this. The naive way is to just pick up one stone at a time and manually check it against every single joule you know about. Step 1, pick a stone. Step 2, scan all the joules in your joule string to see if there's a match. Step 3, increment your count if you actually find one. It's exactly like having a massive box of stones, pulling one out, and then rummaging completely through a separate box of joules just to see if they match. And then, you do that entire rummaging process all over again for the very next stone. You grab a character, ask, is this in the joule string, scan the whole thing, and move on.
And honestly, that exact rummaging process is exactly why this approach is a massive trap. You hit this dreaded O of n times m time complexity. Why? Well, for every single stone, let's just call the total number of stones n, you're doing a linear search through all the joules, and we'll call the number of joules m. If you've got a huge list of stones and a huge list of joules, you're just repeatedly scanning over and over again. Like the folks at AlgoMonster point out, using the string directly for membership checking works. Sure, it's functionally correct, but it's incredibly inefficient. This nested looping just becomes a severe performance bottleneck the second your inputs start growing.
Which brings us to section 3, the optimized hash table approach, the optimizer's tool.
So this is where we bring in the specific data structure that's going to solve our bottleneck and completely transform our code's efficiency. We turn to the hash table. As defined by the Carnegie Mellon University Database Systems lecture notes, a hash table implements an associative array, abstract data type that maps keys to values. But here is the real magic. It provides, on average, O of 1 operation complexity. That is an absolute game changer for this problem. Instead of linearly scanning your joule string every single time, you just load your joules into a hash set once. Then for each stone, you just ask the set, hey, are you a joule? And it answers instantly, in constant time. It maps a key space into a smaller domain so you get incredibly fast lookups.
To see how this plays out in the real world, I saw this computer science discussion thread on Reddit that highlighted the logic perfectly. One user put it like this: you'll spend far more time repeatedly comparing values across two arrays than you will hashing once and doing O of 1 lookups. So the point here is that the initial overhead of creating the hash set, which takes O of m time, pays for itself massively because you entirely eliminate that endless nested loop. Engineers overwhelmingly prefer hash sets over linear string searches for this exact reason. Now, to be fair, there's a slightly advanced debate in our sources that's worth bringing up.
Some developers argue that, hey, since we only have English letters here, you could just initialize a fixed-size 256-element Boolean array to represent all your ASCII characters. You just mark the Joule characters as true at the corresponding ASCII index in that array. And technically, for a strict ASCII constraint, that array approach is blazingly fast and avoids any background hashing overhead. But, as the source discussion points out, the hash set approach is still the clearest, most extensible logic to use in interviews. The Boolean array is a clever little optimization for sure, but the hash set clearly communicates that you understand efficient lookup structures, and it scales super easily if the problem is later expanded to include, say, full Unicode characters.
All right, let's get practical in Section 4. Python solution with code, from concept to execution.
Let's actually transition our hash table optimization into code and see it in action. Take a look at this beautifully elegant one-line Python solution. Return sum of char and set of joules for char and stones. I mean, this is just brilliant. First off, set of joules converts our string of joules right into a hash set. That pre-processing step happens exactly once. Then the generator expression for char and stones iterates through our stones, and the real magic happens right at char and set of joules. Because it's checking a set, this is an O of 1 instant lookup. Python evaluates that statement as a Boolean, and finally the sum function wraps the whole shebang up to give us our final answer.
If you want to see exactly how that Python evaluation works under the hood, let's trace it through an execution table based on AlgoMonster's breakdown. Let's say our joules are lowercase a and uppercase a, and our stones are A, B. For that first stone, lowercase a, the set lookup returns true. Well, in Python, true mathematically evaluates to the integer 1, so our running count becomes 1. Our next stone is uppercase a. It's in the set, so that evaluates to true, which is 1, bringing our count to 2. Our third stone is lowercase b. That is false. False evaluates to 0, so the count stays exactly at 2. By summing these Boolean values directly, we get our total count without having to write any bulky, messy if statements.
And finally, Section 5, Summary and End Credits, wrapping up. Let's do a final breakdown of what we've actually achieved today. Looking at our final big O complexities, our time complexity is now O of n plus m. We spend O of m time building the hash set of joules, and then O of n time iterating through the stones. Honestly, this is a massive structural improvement over that O of n times m brute force trap. Our space complexity is O of m because we do have to store the unique joule types in our hash set. So if you remember one thing today, make it our key takeaway. Hash sets transform O of n sequential searches into O of 1 instant lookups. The moment you realize you're doing repeated membership checks, that is your ultimate cue to reach for a hash table.
Which brings us to our final thought for the day. How will you apply O of 1 hash table lookups to optimize your next project? Whether you're navigating your next technical interview or building scalable systems at your day job, identifying these logical bottlenecks and applying the exact right data structure is absolutely a game changer. Thank you so much for joining me on this explainer. Keep learning, keep optimizing, and I'll catch you next time.